So it's my great pleasure to host Ji-Ung Lee, my previous colleague, also my previous co-author, hopefully future co-author. So he's a final year PhD student from UKP Lab, University of Darmstadt, Germany. And his research focuses on effective model training with user feedback while jointly meeting the user's demands. And that involves approaches that require data sampling without knowing the true label, which we refer to as active learning, and making better use of the available data, curriculum learning, and efficiently incorporating user feedback into active learning. He also co-organized InterNLP, stands for Interactive NLP workshops. One was at ACL and one will be at NeurIPS this year.
There's still time if you want to submit.
Yeah, so if you want to submit to the workshop, you're still welcome.
Deadline is 2nd of October.
Yes, so the stage is yours. Thanks.
Yeah, thank you for the nice introduction and thanks for having me in person. It's really great to be able to travel around a bit again, meet people in person. So yeah, I called this talk Facets of Efficiency in NLP, and most of the stuff was motivated in a seminar. Oh,
That's right.
okay. Should I just unmute myself or should I just go there?
I think the microphone is over there.
Oh, the microphone is
Here, somewhere here.
yeah. Oh, it should be everything. I can try to change seats over there. Is this better? I don't. So the people in Zoom have to tell us. Is it better here? Okay, yes it is. Okay. Great. Then yeah, I said most of the stuff we did there was basically sitting together, trying to think about what kind of methods there are in efficiency and how we can categorize it, and we ended up writing a survey together. And most of the things, or some of the things I will present here are based on the survey, and some other works I will present like my own works, and some practical tips I will also give at the end. So why do we need efficiency? And if you have followed up the developments in natural language processing, you will notice that the number of parameters of the models have been like growing hugely over the years. So you may notice this is an exponential scale here, and you basically get a linear line. And this is mostly due to the paradigm that more parameters just lead to a better performance. However, this kind of also leads to several issues. So first of all, this really burns a lot of resources, and it also costs a lot of money. I think GPT-3 was estimated to cost like $12 million, which is really a huge sum for a single model. And as noted by Emma Strubel et al., this also leads more and more to increasingly high carbon emissions. And some people also estimate that NLP or AI may take up to like 2% of the total carbon emissions in like 10 years, which is like getting bad with the climate change and everything that's happening right now already. And the second problem is that we are actually hitting a hardware wall. So the hardware cannot really keep up with the current scaling of the models. And at some point, we will have to go more efficient if we want to get better models. And finally, as already said, the models are really expensive to train, and this makes it difficult for us researchers to also work on such huge models. And I mean, this is just also more like a self-preservation thing, to be more efficient if we also want to keep up with the research. So to categorize all the different approaches that exist in NLP, we basically try to look at the whole life cycle of an NLP model and where efficiency can come into play. And there are basically various stages where efficiency approaches have been developed and are being used. And you can see all of them here. And at the end, we also, of course, have like evaluation and model selection. So during all of these stages, you will find some approaches that will try to improve efficiency. And I will first give a brief taxonomy and what kind of approaches are there for each of the stages. And you will see that there is a lot of work in there, especially in the inference side. And you probably know several of these approaches that are definitely more popular. And here we try to look at the things from the perspective which part of the life cycle these approaches are trying to make more efficient. And in this talk, and my own research is basically more about the data collection and pre-processing part. This is what we'll be going into now. And by the way, so if you have any questions, feel free to raise your hand or ask them, or write it in the Zoom chat. I think I will be able to see it and just have it like, yeah, during the talk. So one of the things I've been working on is active learning, and here the main idea is that we are trying to improve annotation efficiency by selecting instances for annotation that would help the model the most when actually labeled. So the tricky thing here is we don't know the actual label, but are trying to find out which data is really helpful for model training. Another part that has been brought up more recently, if you think about it, actually it should be kind of like obvious to do it in the data processing, like removing duplicates and things like that. But especially recently, there have been various works published that show like existing data sets still have like bad filtering processes, especially if they are like semi-automatically created. There was a larger audit of machine translation data sets for Paracroll by Iryna Gurevych et al. From Google, which was quite cool. And they also find, for instance, that many languages are kind of mislabeled or contain actually English text because it was like done automatically. And yeah, the last part is basically curriculum learning. This also tries to make learning a bit more efficient by selecting a different ordering of instances, and the idea to make the conversions better, which will implicitly lead to all right. Yeah, there is also prompting coming up recently, but I will not go into detail on that because it's like, so each of these things I've shown in the slide before, they have like, it's a huge field that is like growing constantly, and you will probably find a survey for each of these subfields as well. Okay. So one fundamental question, I guess, is when we go into data processing, and the question is like, isn't more data always better? And the thing is, actually, that's not the case. And this becomes more apparent when we look at the whole picture. So if we are limited on the budget, and then you have to think, so should I increase the model size, so basically the amount of parameters in my models, or should I increase my data set? And there's a really cool work from Hoffman et al. This is the Chinchilla paper. And here they tried out different token sizes for training and different parameters. And as you can see, for each number of tokens, there's like a different sweet spot where the loss is the lowest during training.
What's the X and Y? My eyes are.
Yeah, so the y-axis here is the training loss, and the x-axis is the number of parameters. And the different colors are different amounts of training tokens. And I mean, it's a lot of experiments that they did, but this is really cool because, what's the question?
I think Shad was asking a question.
So I don't see a question.
Okay.
All right. Yeah, and so I mean, this makes you think a bit more about efficiency and how to choose like a model size and the amount of parameters. And
Was it the sort of result of Chinchilla paper, in effect, using a much smaller model with much more data compared to the state of the art was a better idea?
Yeah, they did like various kind of experiments, and they also trained like a very large model, just because they like for comparison and so on, but they found like actually having a smaller model with the correct amount of tokens is actually better than just increasing the number of model parameters and so on. Yeah.
Better by means of accuracy.
Better in terms of accuracy.
Yeah.
But they also do different evaluation. I will come to that later. All right, so now I wanted to present an approach we published this year on improving the efficiency during data collection. And this approach is called annotation curriculum and was done by Jan Christoph and me together with Iryna. And here the basic idea was just happened when we were all in lockdown during the pandemic, and COVID was like a hot topic to start working on in NLP. A colleague of us asked us to do like some annotations, and he basically gave us like Excel sheets with hundreds of tweets where we basically were asked to classify the emotion in the tweet. And so we started doing the annotations, and what we noticed is that we're actually skipping a lot of these instances and jumping back. And the whole idea was that we can make this better. If we order the instances in a good way, we can just start at the beginning, go to the back, and that will save us a lot of time. So the whole idea here in this work is basically if we show the same set of instances, once in a random ordering and once in a proper ordering, that people who see the instances in a proper ordering will have a better intuition into the task and need less time and have a higher annotation accuracy. So to do so, we first define a strategy, and here we go like a very simple one. We try to order instances from easy to difficult, and we then evaluate different estimators to measure the annotation time. So we have a look at heuristics as well as interactively trained models. And after the study, we also always evaluate the accuracy. And here it is really important that we cannot evaluate the accuracy during the study. So we cannot use the accuracy as an estimate to train our interactive trained model because we don't know yet. So we need like annotations from 5 or more people to compute if it's like correct or not, since we do not really know the label. And that's the whole idea behind it.
So when you said it's sorted from easy to difficult,
Yeah.
how do you define that? Is like the amount of time it takes an annotator to
Yeah.
give an answer? Or
Yeah, so that's what we are basically trying here first. So we are trying to find out what are data sets, and we are looking into annotation time. And unfortunately, there are not that many data sets that report annotation time, but we use this here as a proxy for annotation difficulty. And here we basically ran experiments where we try to find out models and heuristics that are good at sorting instances by the annotation time. We basically have an easy instances first strategy, and we have 4 estimators. We evaluate 1 random ordering, 1 heuristic, 1 interactively trained model, and 1 gold ordering, which we crafted by hand. And now the tricky thing is to decide how to control the annotation difficulty. And for this, we use the COVID Live data set because at that time, so we wanted to ask volunteer participants, and COVID was a hot topic last year. We were thinking, yeah, so people will definitely know something about it. And so the COVID Live data set, yeah, I will give some examples in the talk. I think it will be more clear once I explain the data set. So yeah, here you have tweets, which basically are misinformation on Twitter. Oh yeah, this will also come in a moment. And so each tweet is annotated with a misconception and a stance. And I will also show an example in a second. And here we basically filter all tweets that have a positive stance towards the annotated misconception. And so now to control the difficulty, what we basically did is we show the tweet and we show 6 misconceptions. And the idea is that the annotator is supposed to select the tweet that has the most fitting misconception. And the thing is now that we have 5 additional distractors, and by switching them out from similar to different ones, we can control the annotation difficulty. And
So the 5, 6 extra things you're showing, are they categories? Are they other examples?
so misconception is like, I will just jump ahead a bit. I can show you an example here. So here you see tweet and the 6 misconceptions. And the misconceptions are like a bit more broader theories or hypotheses that would categorize different or group different tweets together into a single category.
And do you have the option of none of the above, or is the tweet always one of these?
It's always one of these because we have the gold misconception that was annotated by experts. And I will quickly explain. Oh yeah, I guess we can skip the animation. So what we basically did was we created 2 sets of misconceptions for a given tweet and a misconception, and one that consisted of misconceptions that are very dissimilar, and one which are very similar. And so now by successively removing a dissimilar misconception and adding a similar one, we can gradually increase the annotation difficulty.
So when they're similar, it becomes much easier.
When they are similar,
much more.
Yes, yeah. So I will also go into more detail. So this is actually the correct misconception that was supposed to be annotated here. And here we have basically 4 misconceptions that are very dissimilar, and one that is somewhat similar but has like the complete opposite meaning. So this would be like an easy example in the annotation class. Okay, any more?
I just have an immediate question.
Yeah.
So it doesn't seem very practical.
Yeah, it was so the idea.
In real life, you cannot really sort the annotation examples. Like I would put some similar ones. I would some.
Oh yeah, so the goal of the study was to first of all just see if the ordering actually affects the annotation performance. Since we didn't find anything, it somehow makes sense that if you order instances, somehow in some way, that people may be having an easier time getting into the annotation path. And I mean, the whole idea is to implicitly train the annotators. But so we couldn't find any work that actually did it. And our goal was to have like a clean user study set up where we basically could see like, I mean, it's not very efficient. We are like having 40 participants annotating 50 tweets, all the same 50 tweets. And I mean, you wouldn't get 40 annotations for one instance usually during an annotation study. But the idea was basically to see if evaluate different orderings and see if there is like a significant difference in time and accuracy. Yeah, so yeah, let's actually go into the user study setup. So we selected a total of 50 tweets here, have 10 instances which we use as control instances. And these are given to all our 40 participants, and they have all the same ordering. So this is just that we can make sure all the different groups are compatible against each other. And we then split our participants randomly into 4 groups, and each of them is basically assigned to a different strategy. And here you can see the results. So we measured the total annotation time, the average annotation time per instance, and we also have the standard deviation. And so what's actually cool, what we found is that between the random ordering and the gold ordering, we see a huge difference, which is also statistically significant. And so here it's like the difference is 800 seconds for 50 tweets. So I mean, people argue, yeah, maybe you can get like 2 coffees in that time. And I guess we are still eager to see how this scales up. So this would be our future work.
So the total ratio is almost 2 to 1, right? So 1,000 to 1,800, but the mean is a lot closer. Why is that? Does it mean just the total overhead?
The mean is just the average time. So on average, people needed 20 seconds to annotate one instance.
Right, 21 versus
21 versus 27, but you also see that the standard deviation is Oh, rather high now. But the good thing is that the groups are actually very comparable. So when we compared the groups in terms of the control instances, there were no significant differences. And yeah. All right. So what we can see here, the gold ordering is actually significantly better than random and the injectively trained model. And what's also cool is that the heuristic is significantly better than the random model. So which basically means you could kind of try to automatically order it just using the word MLM score. And hopefully that would lead to a substantial increase in annotation time. I think one thing that should be noted is that actually none of the strategies we evaluated were worse than random. So at least we didn't find anything that makes everything worse, which is, I think, a good thing. So yeah. Unfortunately, in terms of annotation accuracy, there were not significant differences. One thing was we thought maybe the reason why this could be is that we had voluntary participants, so I personally participated as well.
I don't remember, but I guess I do.
Yeah, and we figured people were basically really eager to finish the task properly. Which kind of explains the high difference in annotation time sometimes. But the differences in accuracy are more or less similar, so there are no significant differences. We are thinking if we put everything onto a crowdsourcing platform where people are really trying to optimize the annotation time, we may see different numbers in terms of accuracy, but we are still working on that. We'll have to evaluate this future. Yeah, to sum up, so we could confirm our hypothesis gladly for annotation time, but not for annotation accuracy. Yeah, so I don't see any more questions. Was the question about the easy and hard example clarified? Just to check back from Ali.
Some examples.
Yeah.
Well, for this particular task, it was just how close the
choices were. Yeah. So that's the whole idea. And I mean, the tricky thing was that we needed something where we know the gold label from the expert, because we needed something to evaluate the accuracy. And yeah, then we needed something to control the annotation device. Okay, then I will move on to the second part of the talk. So here I will try to give an overview of how we can quantify efficiency in a more practical way. Try to give a couple of tips what we can do ourselves to make our experiments more efficient, and then we can start the deep discussion. So to measure efficiency, there are various kind of ways. People have been proposing flops, so the number of floating point operations. Here it's kind of important as a side note that you do not confuse this with the floating point operations per second. Sometimes you see like flop, then slash s, and that's actually the speed of a GPU, for instance. Then the wall clock time, and some people also measure power consumption or carbon intensity, and yeah, the final and probably all deciding factor is money most of the time. So to compute the flops, there are several formulas. Unfortunately, there is no really go-to formula, so I will send you the slides later on. I link the papers, so you can have a look at the papers later on. And here I will just briefly discuss 3 approaches that have been proposed over the last 2 years. So the first one was from Kaplan et al. 2020. They do different approximations. I think one thing you can just remember as a rule of thumb, they propose to use 6 times the amount of parameters multiplied by the number of training steps or the tokens. That's like a real easy to use rule of thumb. And I mean, they have like different approximations they make. And at the end, they boil it down to like the simple formula.
So
Yeah.
that means that they're assuming that a single training step is linear in the number of parameters, so, right? So there is no, for example, quadratic relation to compute each hidden state value.
So that's what they approximate in the end. But I mean, I guess one of the issues with transformers is that they have a quadratic dependency on the sequence length.
That's
I
right.
mean, that's many things people are trying to tackle. And I remember seeing a paper recently that was beating S4 on the long range arena task. If I find it, I'll send it to you now. Here, it's really cool. But the idea is, so if you have this number or this model and this much data, how can we roughly estimate how much floating point operations this will take to train? So that's the whole idea. And I guess it makes sense if you have like a fixed budget and you try to find like how large can I make my model and how much data I can use for training. And then you would do kind of this kind of computation. And that's the same thing they did for Megatron LM. Here, one thing they dropped is the embedding size. So, I mean, they argue like the embedding dimension is usually something like 50K, and it doesn't matter if it goes up to like 10 to the power of 13 or something. It's insignificant. And the chinchilla paper is basically the last one. That's the only formula that explicitly shows uses number of heads. It's a bit more easy to use, I guess. But overall, I think they do not deviate too much from the Kaplan 2020 approach. And I mean, as a rule of thumb, if you don't want to use a complicated formula, you can just think of, that's the number of parameters times 6 times the number of tokens.
Well, why do people use these approximations? Can't you just run your network on a serial machine?
Yeah. I mean, that's what can you do? Yeah, but you don't know that in advance. So you don't want to run it every time just to see how many floating point operations you need. So
Yes, first.
Yeah, that's why people are trying to roughly guess how much it will take. There are some similarities. I think the most important thing is that people usually calculate that the backward pass is twice as expensive than the forward pass. And then I will just show a quick example on the Roberta model. So we have a bunch of parameters we can set for the computation. And so as you can see here, the one that is like really approximative is the one by Kaplan et al. We basically take the number of parameters, multiply it by 6 and the number of tokens. So here, number of training sets. And for the other more sophisticated formulas, you can try to also, depending on the batch size and the task, play a bit around with how it would perform on fine-tuning, how it would be on inference if you drop specific forms of the formula. And I mean, in the end, they are more or less, at least these two are more or less quite similar. So,
what is the gold number for these? Do we know?
I will show an example soon where I just measured the number of blobs in an experiment and compute this. So this is just a computation example. I was actually working on a small web application where you could put in all these numbers and get the number of flops back. But it's more like a weekend project, so it will take maybe 1 or 2 more weeks to upload it somewhere.
You can just do Excel sheets, right?
Yeah, you can do it also with Excel sheets. All right, so so if you want to actually do it in practice, you can use something like DeepSpeed. That's a library I found the most easy to use and set up. And so if I here I basically trained a tiny bird model because it's something that runs locally on my machine as well. And here you can see the differences. So what the DeepSpeed measures is like something to 1 to the power of 10 to the power of 11. And I think the closest one is the Megatron LM, because that also doesn't consider the embedding layer. Chinchilla is somewhat close as well, I guess, but a bit more. And I mean, DeepSpeed is actually quite easy to use. You can just install it and start the flops profiler.
So DeepSpeed actually gives you the real
It measures the flops, yeah.
That's great.
There are other things from PyTorch and that use some NVIDIA libraries. The issue is one of them, they already announced that they won't support it anymore, and the other one is like you need to pay for it. So yeah.
So all of the methods actually overestimate the flops, because overestimating is less risky than
It's less
underestimating.
risky because you know, like, okay, I overestimated it, and my experiment will run through and safely finish. It's better than at some point.
What's concerning is like Chinchilla, 10 to the 11 versus 10 to the 13. They're overestimating 100 times.
Yeah.
So if you were
And
trying
actually
to guess training times, 1 day versus 100 days is a big difference. So
Well, it's a big difference for us. Or than estimated.
I don't know. Yeah.
I mean, so the thing is, this was also a very small model, where basically, I guess, and I didn't use any additional. I'm not sure. Yeah, maybe. It could be that there are some additional optimizations. No, I don't think
So is it like an active research area?
this is
to
actually,
estimate flops?
yeah. I mean, people try to go with something that's like a rule of thumb. What's a bit unfortunate is that ACL recommends to report flops, but I mean, there's no go-to formula. So I think what you should do for your experiments, just use something like
I mean,
you can just measure it.
mine wouldn't be just train a regression model, giving all this number of parameters, number of paths, and then
Yeah,
fit it.
it's a good question. I guess
It seems very easy to do.
I mean, I also was going to suggest so in the backward pass, you basically have to create this computation table. You're basically writing a compiler when you're writing PyTorch or its variations. So it's very easy to instrument that compiler because it knows every primitive operation and say, we know how many flops each primitive operation takes. So it should be easy to actually calculate it just by looking at the model code.
I guess it somewhat depends, especially when people are trying to develop more efficient architectures, where I don't know, they have things like
You can have dropouts, you can have traffic networks, you can have
things
some
like that, and
uncertainties.
True, but the
sparse activation.
deep learning compiler has to compile all of that. So while it's compiling it, it can also write down, I'm doing
Makes
this many
sense.
times this operation, etc.
That's true, actually.
The big uncertainty there is that you don't know what NVIDIA library does behind the scenes when you actually multiply two matrices.
Yeah.
So there is not a single matrix multiplication algorithm. So
and I mean, depending on the GPU you have, and they are starting to build in like very specific modules that can deal like with the brain float, half precision stuff, and then it becomes really tricky to roughly estimate how. I mean,
then all the formulas will change again.
Yeah. So I mean, people just try to come up with some good approximate formula as a rule of thumb, to get a gist like how much you need before you run the whole experiment. All right. Okay. Measuring wall clock time is fortunately much easier. I would recommend to use perf counter. One thing you should think about is that you should not use process.time because that will not include idle time. And here you can basically see the differences. So this was the code from before. basically training a tiny bird model, and it takes around 14 seconds on my machine. Time is similar, I guess. So if you get the time delta, and it's about the same as birth counter. And for the process time, you can really see that this is like 3 seconds, where apparently the process didn't really do something, but maybe it was doing some computation in the background. All right. And so, I mean, what would be a cool feature? That's like still a very open question, and that also goes a bit more into the discussion we just had, is how we can approximate the actual runtime if we have a model. And I'm just showing a couple of data sheets here for all the GPUs, and it becomes more and more complicated because of course all the hardware people are also trying to build like very specific modules where some operations can be done really efficiently. So unfortunately here it's yeah, a tricky thing, and I don't have a good recommendation how to compute the wall clock time ahead of your experiment. All right. So the final thing I will briefly go into is the power consumption. People are trying to also estimate that. Some people try to use like electricity meters, but that's not always an option, especially if you have data centers where you have to estimate things like cooling or networking costs. However, there are a couple of libraries, which is kind of cool, and there are also libraries that try to break down the power consumption of individual components in your machine. So I linked one here. You can check it out if you're interested here in that. And one thing that is quite related to power consumption is the carbon intensity. So I mean, it's I guess more hype to report carbon intensity, but it really depends on the local energy mix. So you have to keep in mind that it's noisy metric. And when you read somewhere that carbon intensity is reported, you should definitely ask or check if there have been multiple runs and what they actually report, or if it's just like, I don't know, they just do it like once and report the number because it sounds cool to report your CO2 footprint of the experiments. I will show an example here where I basically run the same code that I used before, so training a tiny bird model on I think it was sentence classification. And if I just use code carbon, which is quite a cool library that is for that, you will see, for instance, for Canada, it's almost half the emissions than compared to Germany. For some reasons, they seem to have a better energy mix.
We don't use nuclear energy.
Yeah, that's the issue. Yeah, so there are more and more cool libraries you can use, and I mean they are also all really easy to use. So, if you're interested in doing that, just add them to your experiments. The number of flops, and it's definitely a recommendation by the ACL guidelines to report grades on this. All right, so let's come to the end. One thing you should definitely think about when doing experiments in efficiency is you need to keep in mind that it's basically always a trade-off. You are trading off often something like accuracy against the number of training steps. And the main question is, how do you select a model that maybe is more efficient but has a worse accuracy? Unfortunately, it's always really depends on the situation. What you can do is you can draw things like Pareto frontiers, and these basically allow you to basically see at which point of the curve basically the best model is. Use them to select the model you want to use for, I don't know, inference or in an application. Okay, so let's maybe go into briefly what we can do ourselves for our experiments. Just try to avoid running experiments over and over. This was a mistake I did when I was basically starting my PhD. I forgot to index my data, and then
Yeah.
I wanted to run analysis, and I couldn't recreate it anymore. So just index your data, store the predictions. I actually also see with a couple of students who started to use weights and biases a lot. I mean, it's a great tool where you can see like loss curves, but you should still remember to store your predictions as well, because you will need them for error analysis. The second thing is to use small data sets for debugging, and implement a small baseline model first, just to get basic performance. But I mean, it sounds so easy, but not many people actually do it. Like,
I know.
yeah, so using small data sets for debugging is generally good practice, because it will save you a lot of time, and it will save the others a lot of time. And there are various ways. So I created a couple of data sets and uploaded them in the GitHub link I will show later, and you can just check them out if you want to. When you generate data sets for debugging on your own, keep in mind that you try to generate them in a way to go for basically some basic things. So to see if your model is capable of overfitting to the data, or if it can generalize well, and to see if there's like some potential leakage in your code, where it's like a bug or something. And so yeah, first of all, the data set should be small, and you can just sample a subset of your data, make sure that you fetch one example of each class, use different examples for different splits, and just get enough examples to run through backward passes, just to make sure that every training routine is running more or less correctly, and run a simple baseline model. And here, so yeah, I mean, it's not that common anymore in NLP to have like fixed features and train a model based on that. But if your setup is something like this, you can also just sample features like from a Gaussian distribution. Just make sure the centers are somewhere differently located, and then you have like your two classes.
So when you mentioned debugging dataset construction, are you talking about selecting a subset of your real dataset, or are you talking about creating an artificial dataset?
I mean, you can do it however you want. I mean, usually, if you have like a general task like sentence classification, it probably you won't have to recreate a debugging dataset over and over again. Just easy to have one sentence classification task. If it's something more tricky, so I have a colleague who works in differential privacy, and he samples from his data actually, because yeah, it's very different what he works on from the usual NLP tasks. The thing is, you should just make sure that you know what you can expect from the model, so that you can always see how well your code is performing. Right, so yeah, as a small example, so the thing I uploaded on GitHub, it's a small sentence classification task. I just sampled sentences from what we did. Had some minimum and maximum length, no overlap between classes, and I trained a tiny bird model on this, and I made like 4 splits. So the simple one is just evaluating on the training set to see if the model is capable of overfitting. The second one is the transfer one, where you just use different examples. The third one are outliers, where you have mislabeled instances, and you have to make sure your model needs to basically mispredict everything. And the final one is just a mixed one, where you can see if it's like reaching the expected performance.
So can you explain the third one again?
Is
the training set mislabeled, or the test set?
The test set. So these are basically all test sets. Just to make sure that your model is somehow not learning something it shouldn't. Yeah, and I mean it's quite fast to run. So as you saw in the other slides, so all the setup takes like 14 seconds, and that makes it easy to debug your code without putting everything in the class. Okay, now let's just come to a quick discussion. I mean, efficiency is really still a very open research topic, and there are a bunch of ways to do more efficient NLP. And quantifying efficiency is unfortunately also not very easy, but there are actually many things we can do on our own to save resources. As said, here's the repository with all the experiments I showed, and you can run them yourself. And yeah, as said, so there will be a bunch of works when you try to go into efficiency. So for the paper, we surveyed more than 250 papers. But like each of these fields also have surveys of 300 papers, so it's really a lot. But it's still not, yeah, and that's not really exhaustive. Maybe one thing I wanted to bring up at the end is the actual question if efficiency is really helpful. And I think when you look at the release of Dall.E 2 and the release of Stable Diffusion is kind of a very good example. And so they are both AI image generators based on prompts. So the main idea is you enter a prompt and the model will generate an image. And Dall.E 2 was released with a wait minutes, with a rather long time, I guess. And Stable Diffusion, what's kind of cool was the model was very efficient, so it will run as long as you have some sort of graphics card with 4 gigabytes RAM. And so what happened, of course, people start using Dall.E 2 as well, but if you look into Stable Diffusion, you will get a lot more pictures that are generated, and some look like really amazing. You have a picture of I think it was like Jevons Zuckerberg was the prompt. People trying to get like Pokemons done in the real image. But I mean, the main question is, and this brings me to my last point, is basically Jevons Paradox. And the question is efficiency always helpful? And Jevons was a guy from, I think, the early 20th century or something like that, when people tried switching from coal to fuel. And so he was basically saying, so people argued like, yeah, like oil is more efficient than coal, so we should use oil. And he was saying, no, that it's actually not really a good thing because that will decrease the cost of using oil. So people will use it a lot more. That's the whole thing. So maybe one thing you should think about when working on efficiency, always take it with a little bit of grain of salt, because increasing efficiency can actually lead to a higher demand, which increases the overall resource consumption. And we can see it like quite often, I guess, for instance, with Google Translate and everything. I mean, I tried it out, it's really amazing because it works on your phone, but I guess I was using it much more. I mean, in the maybe 10 years ago, I would just have brought a dictionary to Turkey and use this instead of NLP. And yeah, this is basically the end. Maybe one fun example, a friend of mine sent me is like a commercial for a coffee machine that advertises AI because it ranks your favorite coffee. Yeah, thank you.
Thanks a lot, Ji-Ung. So, does anyone have any questions?
I was gonna, the first part of your talk about annotated efficiency, I was gonna make a comment there. So you tried sort of easy to difficult sorting of examples. We found with Emrecan, we're working on annotating Turkish morphology. So this is the problem where you're basically looking at a long, complicated Turkish word, which may have more than one interpretation, and picking the right. So we found that if we basically gave people just text, and every time they're basically trying to disambiguate a different word, they have a lot more difficulty. But for example, if I just gave you one word, one ambiguous word, and lots of different contexts it's used in, you sort of become an expert in distinguishing that word, and you become much faster. There is much less context switching.
Yeah.
So I guess to generalize that, I would say maybe orthogonal to easy to difficult sorting. It might also help if the annotator is basically faced with the same problem over and over again, same type of ambiguity over and over again, so they distinguish it instead of switching to different types of problems.
So I mean, there are a lot more aspects regarding annotation difficulty.
It's like automating the brain, so every time for each example, the brain tries to.
So I mean, one thing is like you can also look into annotator motivation, and I mean, if you go into education, there are like various theories like the zone of proximal development. It shouldn't be too easy, it shouldn't be too hard, and you don't want to bore your annotator or frustrate them. So there are several factors where it makes sense to consider them. Yeah. And yeah, but I guess at some point you want to switch to a different word. So maybe you should select select them maybe based on, maybe it would make sense to have a similar context and then a different word, and then you can switch it on to something like that.
Yeah, actually, I was gonna ask about this difficulty. Is it stuff?
Yeah, I mean, it's funny because all the works in curriculum learning were basically trying to make model learning more efficient. They often assume like easy instances first strategy, but that's actually, if you go into human learning, I think they are way past that already. So they're really trying to look into different dimensions of what is easy, what is difficult.
Yeah, I was gonna ask, why didn't you look at some data sets with some eye tracking data or EEG data to begin with, so you would know what is easy and what is difficult for sure? Or
Well,
was that available or not?
no, so we looked at various data sets, and one data set we found that had something like annotation difficulty annotated was one from Christopher Taubman and Johannes Daxenberger, but they had like this staged approach where I think they used ANT, and they had like 3 different studies where basically the users were shown only easy examples in the first study, then more difficult ones in the second study. And we didn't find anything where we could like just easily extrapolate the difficulty. And so for the user study, the tricky thing was that we have instances where we can control the difficulty and order them in a different way, basically. And also we didn't want to make the task too difficult or too frustrating, because all of you want to take it basically, and yeah.
And some of the heuristics only work when you have like multiple choice annotations, right? That's how you.
I mean, it really depends on the task. If it's like maybe for summarization, we can also use something like language models for that should work. Yeah, but I mean, we also have a more marking formula. We try to give like a general framework. In the paper. Yeah.
So I have another question. So all this approximation of loss studies, they are dependent on an architecture, right?
Yeah.
And they report like, for this architecture you should use this formula, for this architecture you should use this formula.
Actually,
no, it's more like,
I don't think it's architecture dependent. That's
Well,
why you're counting floating point operations. So the architecture affects how many of these you can do in parallel, but the total number of individual adds and subtracts and multiplies won't change between 2 architectures.
But the formula would
I mean, they assume transformers as the base model.
So the formula, the answer won't change based on what GPU or CPU you run. Because you're basically giving me, okay, here's a model, here's a mathematical expression I want to compute. Matrix multiplies and batch whatever, and I can count how many additions and subtractions and multiplications I need to do. The wall time will change between different GPUs, but the flops won't change.
What they are basically doing is showing the they are assuming the transformer architecture. So I guess that's the most thing where all are cool. And I mean the issue is the flops are.
When you said architecture, did you mean the model architecture or the GPU architecture? I think we took it in different.
Yeah.
Yeah, I pure architecture, but I realized that it makes more sense to answer from the perspective of model architecture.
Usually this is about the amount.
Because I thought it would make some difference to use some NVIDIA internals.
Oh, okay. No, they just assume a transformer architecture, and you can also see different computations about for model size and so on. Yeah, I mean, it's probably nice to do this computation once by hand, because it forces you to really dive into transformer architectures and what actually the dimensions are in the hidden layers and everything, because much of this got like just, I mean, people report the number of heads, number of layers, and maybe the hidden dimension, and that's usually the total amount of dimensions.
So from your survey, what is the feature? What is the challenges, and what should we focus on for if you want to work on efficiency in NLP?
I mean, I think one very open challenge are long documents, because that's really tricky.
Transformers, right?
Yeah, for transformers. I mean, people were already not happy with all the RNN architectures, and thought like transformers can do longer documents. Unfortunately, not really. Yeah. But they are so. I think you can kind of go into every direction, because they are like new architectures coming up, moving a bit away from transformers. The S4 paper was really interested. I think it's it's called structured space something, and that's like a whole. Well, I will have to send it to you.
So this is about longer documents.
It's about longer documents. Yeah.
Two of our listeners, both Batuan and Ali, are working on trying to figure out how to do longer documents. So if you have anything relevant,
I will definitely send it to you. Like new mechanisms that try to move away from the self-attention part, which is like makes the quadratic dependency on this concept. That's like the main issue. People are also more interested in trying to be more efficient during pre-training or fine-tuning. So lots of the works you will see here have been on inference. So I mean, if you look at like pruning and distillation, I mean, yeah, there are things like distill work, but usually people do distillation during fine-tuning to make inference more efficient. That's the same for quantization. I mean, if you are really interested, there are also a bunch of tricks people do. So what I could see is like from the larger models, for instance, OPT model from Meta, they released recently. What seems to be a standard now is actually a data deduplication step. So they really try to remove unnecessary data for training, which is cool. That they do it like very explicitly. And some tricks are like, for instance, doing all like the forward and backward passes at half precision, and then just storing the full precision rate. So you're basically using 16 bits to do all the computational stuff, which is more expensive than you store like the 32-bit rates and so on. There are things like that people can do.
Great. Okay. So if there are no further questions from Zoom, let us thank the speaker once more. Thanks for coming. Really great lunch. So we will have some one-on-one meetings.